Well, thanks, Karen, and thanks very much for organizing this program here and the conference and everything, and having me here. Great privilege. And I told Karen that Frank and I, we are the only experimentalists here, so we are the blurred people who are showing some experiment. Oh, I'm sorry. Okay, the three of us. I'm sorry. So anyway. I try to cover for me, the most important things for metallic glasses right now, what we learn in comparison to colloidal systems and so on, and obviously we show some results for the avalanches later on. And this is a whole bunch of people who are working on it, and on this actually the collaboration will be Johnson at Caltech, and Itamar was here during the conference at the Weizmann Institute, and we have some funding from the DFG and from the European network of vitrified metallic glasses, which is quite nice. So very general, I'd start very general, and you can interrupt me whenever you want, and then the story gets, we have time limits obviously, so the story gets extended or not. Very general, if you look at the dielectric loss for a organic liquid, for example, versus frequency, this is managed by Lunkenheimer and Leudel, that's over 21 decades of frequency. And what you see is, this is very general, several types of losses if you excite the system. One which is called the primary or the alpha relaxation at temperatures around the glass transition temperature, whatever you call it this way, the liquid, which is something related to the viscosity. Then we have at far higher frequencies, we have what we call the wing or the slow beta processes, which show up here as an asymmetry of the alpha peak to the high frequency range. That is something which I call in the beta relaxation or Johari-Goldstein modes, and I will show you what we think, what we know about it actually right now. And then there is even higher frequencies, we call it nearly constant loss or fast processes. This is cage breaking in the systems described by the mode coupling theory, or predicted actually by the mode coupling theory, and then found later on experimentally. And then we have the boson peak, which is something like the remembrance of the system to vibrations and to something which you could call phonons in a crystal. And this purple at the end doesn't interest today. This is just the internal intermolecular vibrations in an organic liquid, for example. So if we want to understand what's going on in liquids and metallic glass, I'll show you in a minute, we have to understand at least the alpha, the secondary, the beta process, maybe the fast process over here, to know what we excite in such a system. And that's the name of the game for us here, to explain a little bit what we know so far.
What is the difference between the dashed line and the bold line?
Temperature. Oh, I show it to you later on. Sometimes this shows up as a real little maximum on one flank, and then in other system that's actually just in a asymmetry. That's why they call it ring. Sidney Nagel talked about it in the first sense also. But there is lots of discussion going on this excitation part here in the frequency spectrum. We have metallic.
If it doesn't show up as a peak, it's hard to say that it's a separate process from.
We'll come to that. That's exactly part of the idea what to discuss today. Yeah.
And how deep do you have to go into the supercooled liquid to see how deep are you in the supercooled liquid here?
That's all above TG. Okay,
yeah,
but below. Well, that's also a good point. In this room we discussed 4 years ago. Jim will remember what actually kind of processes do we have, and when do we see that. Yeah. Deviation from the Arrhenius law at the viscosity and so on. Yeah, we can.
If you have some kind of alpha, presumably it's not exponential relaxation, right?
Okay, if we get into that, and from the beginning on, I should draw a picture maybe over here, which I don't have in the slide. That's the viscosity, the log of the viscosity versus 1 over T. And this is normalized sometimes from Austin Angel to TG. So you have something, a TG over T. So high temperatures is here. And you have some number over there. And then there is these so-called strong liquid, glass-forming liquids, which are more or less Arrhenius-like. This is, maybe it's good I put it on, it's silicon dioxide. Then you have the orthotophenyl, which is the other thing, which is the organic liquid, which goes like that. It's called the Vogel-Furcher-Tammann law over there. And okay, thank you. That's a privilege too. Jim is making light here. Thank you. Anyway, and now you can decide whether the landscape, if you talk in pictures of the potential in the landscape, shows up where this part here deviates from an Arrhenius one. There is, so this temperature, 1 over T, let's call it Arrhenius, deviation from the Arrhenius part. You can talk about what we call the merging temperature, where the alpha and the beta process merge at high temperatures. I didn't want to talk about that actually. I'll show you in a minute what it means. And then you can talk about Tg. This is 1 over Tg, somewhere at some certain arbitrary number. And in the mode coupling temperature, it's actually around the merging temperature. And then there's people in the material science department, they talk about crystallization noses, where this happens. And that's it. So I'm talking here, this is around, let's say, this region or below, okay, where you clearly see the landscape already by forming certain configurations in the liquid, polyeders, clusters, superclusters maybe even, and the metallic glasses, by the way, are in between here somehow.
The boson peak is due to the fact that you have some kind of short-range order in the liquid? Or?
Vibrations in the liquid which are not just ballistic, but they show up later on. Also in the glasses, there is low-temperature physics, which I don't want to cover here. Robert Pohl, Bobby Pohl, and others. Anderson did a two-level system model for that also. Now they think that the boson peak has something to do with vibrations, which are asymmetric. Okay, this is Schirmacher's work, and the colleague in Italy, Ruocco, and others are working on that.
So what are typical glass transition temperatures for these bugs?
I come to that also in typical 300 Kelvin, but it depends on the composition very much. The interesting point of this diagram is this is very universal. You find it in everything which is disordered. So I don't know any example, at least in the liquids, in the disordered system, biopolymers, polymers, metallic glasses, I'll show you in a minute, the others which you don't have these kind of structure. We can't measure dialectically because we have metals. So we built up in Goettingen quite a variety of systems to measure mechanical these objects, okay? And the workhouses today is just this very simple dynamic mechanical analyzer which works with a loudspeaker and has a sample down here. And in the middle there's a little magnet inside coils, and you pick up with this magnet your phase and your response, the amplitude and the phase of the response, and you excite between quasi-static 0.01 hertz to 50 hertz. A newer machine go up to 300 hertz. Then there are other things I don't want to say. Ultrasound, obviously, 5 to 20 megahertz. Surface acoustic waves, I don't talk about it today, but I will talk about these AFM, the atomic force microscopy measurements, which are locally then excite the system, and you can make local modulus measurements. The idea here is actually, since we talked about during the meeting and program and also during the conference about stress-driven or strain-driven, any machine is stress-driven. It's internally regulated. If you say it's a strain-driven machine, okay, the experiment, in the real world, I mean, then there is a feedback loop between the strain measurement technique, whatever you do, and the current, which drives the electromotor or the amplitude of the outspeaker here, so to make it a stress measurement. So there is always internal time clock also involved. And when people say they make strain-driven or strain rate-controlled measurements, it's always a feedback loop inside the machine which regulates the electromotor. Okay, that's something which you have to keep in mind. So that is what we're doing here. We are stress-controlled. So we have the magnet and we have a loudspeaker and it excites the system mechanically. So this one I come later on. here we go. Was quite some time ago. First measurements on this palladium copper silicon system. So we decide between those which are more fragile in the sense of Austrian Angels plot here, more like a orthotorphanol, the Vogel-Friedman law, which are ones which have an electron system which is more spherical, S-like orbital, so to speak, and bonding. And this belongs, palladium copper silicon belongs to those, and those which are more strong ones, which are the zirconium, titanium, lanthanum-based ones, which have a different, more orientated bond-like orientations in the d bonds and d electrons, and that's one which has different strengths and in what we call strong glass-forming systems. Here we do have now the modulus, the loss of the modulus versus temperature. And what you saw just 2 slides before in this general picture, which is on the low frequency side, and then higher frequencies is just turned over to in the temperature domain to the high temperatures for the alpha peak. TG is around here something. You see the wing coming out down here. There is some losses. And if you measure more carefully later on, we found that the losses are getting smaller and smaller. Our frequency here is quasi-static. It's 50 hertz. Okay, and you shift with your frequency. You shift. If you're sitting here, for example, high frequencies, megahertz or something, you're shifting now your whole spectrum through that frequency by temperature.
You're not tracking the peak. You're not tracking the peak or something.
I can track the peak also, okay? This is what we can do actually, but it's not necessary. You fix the frequency and shift the temperature, or vice versa. Fix the temperature and shift and vary the frequency.
But in the middle of the temperature range, you just showed us you're vaguely where this little bump comes that you're calling slow beta.
Yeah. We did measurements on polymers, and to show that actually what the type of measurements we did with mechanically, the electric measurements are the same. Okay, there are some little changes how you excite the backbone of the polymer mechanically different than the dielectric measurements do, but that's a little detail.
I mean, the dielectric constant for a metal should have worked, right?
Yeah, that's why we measure mechanically. This is just mechanically. That's the reason, because otherwise we wouldn't see anything, right? So we always use mechanical excitation to avoid this problem. Although it's bad metal. Okay, now let's try to describe what the picture is, the general picture about all these excitations. And Sylvia Weber gave a long time ago a potential energy landscape picture, which we try to analyze somehow. And you start at the very low end when you quench the system into a glass with positions of atoms which are unhappy. I think Takeshi Egami gave a talk here. Maybe did he talk about that here? I wasn't there. So unhappy atoms means you're sitting not in the right potential minimum, next neighbors to each other, so they're under stress. And the reason why all these properties of the glasses and the supercooled liquids actually happen are due to these unhappy atoms which produce huge atomic level stresses. So the disorder and also the rearrangement, and that's the cause of all that in this kind of lowest positioning of the T equal 0, where the positions of the atoms are located due to this quench. And since the icosahedral cluster in metallic systems, which are very likely to form, they actually are not space-filling in 3D. So if the world would be 6D, then there would be no stresses actually, and there would be stable liquids in icosahedral forms like the quasi-crystals down to lowest temperatures. I don't talk about the two-level systems from Bobby Pohl today. The vibrations we can talk about from Helmut Schober. He gave a talk 4 years ago here, also at that conference. And then I talk about these jumps, these cage-breaking jumps, these strings, and then what we call plastic events. And I say plastic events because we had in this room a discussion a couple of years ago with Jim and others, what we actually call an STZ and what we call a plastic event. and to make it sure that there was some wording problems. And so I try to say plastic events. Sometimes in the slides there's STZ saying. What's going on? We need two different, let's say, qualities. One which is irreversible, which dissipates energy, which is actually the flow of the system in the alpha peak. I showed you the alpha peak, which needs some driving from one configuration into another configuration. So from one meta basin, if you want to say it this way, into another one. But we need a second effect, which is diffusion below TG, relaxation, aging, rejuvenation, and all these things which we discussed also briefly during the conference in the last 2-3 weeks here, which needs a secondary excitation, and this is this low beta process, which is inside, reversible, within one meta basin, reversible. You can go up and down again. You can discuss these aging phenomena in this kind of sense. Diffusion, I show it to you later on, what that means with the beta relaxation. And then you have, this is reversible. You can get out the mechanical work which you put into the system by to a certain amount at least, by a recovery experiment in the entropy. And then you need a secondary effect, or a second effect, which is called the primary relaxation model, is then the alpha relaxation.
Does it mean that these small barriers are of the order of the temperature and the large barrier not, or what?
Well, that was what our French colleagues discussed, okay? Whether you go now with temperature up here, or whether you tilt your barriers by mechanical means down there, is a huge difference. I will show it to you later.
I believe this. My question is, what is the difference between the small barriers, which correspond to beta relaxation, energy-wise, with the big barrier which you have here for alpha relaxation?
If you discuss it this way, I will try to make a point that actually an alpha process is a composure of small beta strings actually. So the energy-wise, you climb up energy-wise up here, up to a certain moment where the local modulus gets zero, and then the system flips over into a new configuration actually. So when you want numbers, or you want?
No, I want just to, if you compare KBT with the height of this barrier.
Yes, this is about KBTG.
Yeah.
Okay, this is about the temperature of where the glass is.
I understand, but your experiment is then typically done at much lower temperature.
Much lower temperature, and close to TG. I show it to you.
What sets the two scales? I mean, now you're postulating one scale for alpha and one for beta, and more or less nothing in between.
Yeah, that's a good point. We come to that in the sense, what actually is the length of the string, and how much energy do you need to excite that? And then there seems to be a rule actually for exciting 5 of these beta relaxations to make one alpha process. Why is this so? I can try to explain in crystalline systems which have 5 different gliding planes, which makes one change in the configuration possible without volume change. And so the range here from one to the next one is not equidistant.
These are supposedly properties not temperature dependent, but these are properties of inherent structure.
Yes. Okay, I misunderstood it.
It's a very, but this is a plot that really ought to.
No, I understand this, but I mean, if you talk about relaxation processes, they happen at a particular temperature.
Yes. But this picture is first of all just the potential energy, of course. Yeah. Okay, since we had so much discussion about the colloidal system, I put some slides in actually from previous work from Peter Bollin's group here in 2006. And they found in colloidal system some kind of a string-like structure and some kind of this kind of octopus or whatever it is, kind of this issue which they call a transformation then also. And what they also showed that if you increase then the rate of shearing and also in our case the temperature later on, that these objects get smaller and smaller. And at the very end, they all have to be ballistic. At the very end, this liquid becomes a gas with Planck constant ballistically the frequency then, so they have the single atom at the end. So there is cooperation going on from high temperatures coming down to low temperatures, and at a certain point the system freezes into a configuration.
Remind me, this picture shows the atoms that are moving, is that right?
Yes. Oh, yeah. I'm sorry. Yes. Yeah, I should have said that. This is just the atoms which move in the whole system. And since
this kind of barrier represents more like an entropic barrier, right, than an energy barrier.
That's a good point. We talk about right now only about energy. Why there is no entropic point? Actually, we can come to that also. That's a very good point.
But the thing that makes this take a long time is not because there's an energy barrier to it. In fact, there's very little energy barrier to move along a string, right? What
This
makes
string
this
is
take a long
moving-
time is that they all have to line up. They all have to find a.
No, the picture is actually that they reorganize into a certain configuration, and then they cool down, and to move then individually one string versus the other string, it takes some energy barrier to overcome then for that motion, okay? But they're not separated. The relaxation
An alternate
is a
picture would-
exponential one.
An alternate picture would be that there's some sort of saddle in the energy landscape, and it's just very hard to find.
Yes.
And so it takes a long time because it's hard to find, not because there's an energy barrier to it, but because it's just hard to find. That would be an entropic contribution. I think that's more what's going on in these sorts of pictures. Maybe what's also going on in yours, but I don't know. But
Let's go on for a moment and keep it in mind, because right now I'm talking about potential energy only and certain configurations which show up. And these configurations, and this was mentioned during the conference already also, is this work from the Weitz and Sparpen group in 2007. They showed when you shear a colloidal system, and then we have certain hotspots over there where the activity, the motion is very large, these red points, and then there is certain strings in between also. Here taking out all the other atoms which are blue here, which are not moving much under these circumstances. And then you get certain correlations. They call it actually transformation zones and also branches, not strings or chains. We discussed, Emanuela and I discussed yesterday chains. And I bring that picture up, which Don Louis already showed to you, which is just a recent review article from Kate Jensen and Weitz and Sparpen. And they see again this autocorrelation function. This is not the quiescence system, this is the strain system. And Don Louis discussed it already, which shows that the whole system somehow at the end has a kind of a autocorrelation. It looks like equilibrium. We cannot see our atoms. It's a pity, but all people who try to do TEM work on metallic glasses and on try to see an STZ, try to see a string, they ended up somehow without success. So what we thought in Goettingen was, let's try a different way. Let's try to experimentally look for this inhomogeneous picture which the colloidal people see here. For example, here it's red points and blue points. And I showed some of the data already a couple of years ago. This is what we call the AFAM, the acoustic atomic force microscopy. If you forget the lower part here, you just have a sample, have a cantilever which has a certain tip. The tip is in contact with the sample. That's a normal atomic force microscope. It tests actually the surface, the roughness of the surface, asperities or whatever, friction, surface friction can be measured that way, and many other things, magnetic forces, van der Waals forces. That's a wide variety of this technique. It works with the recoupling of that system then to a mirror and to the photodiode and so on. You know that. We added to that with the help of Walter Arnold's group in Saarbrücken, an ultrasonic transducer underneath. We excite the sample to a certain way and then look for the bending vibrations of this cantilever. And this way we get information about the contact modulus. So we measure locally with the tip radius in the Hertzsprung contact model. We measure the modulus of our sample very locally. Not on an atomic scale, of course. That's not possible. Because the radius we measure is about 10 times the radius of the tip, and if you think the tip as a sphere, then you have a certain radius there, and 10 times of that is your measurement zone, so to speak, and that's about 10 nanometers resolution.
So what's the typical scale there?
10 nanometer. 10 nanometer, yeah. We have this coarse-grained picture there, and that's the first picture to test the system is actually the crystalline single crystal strontium titanate oxide system, and that's the excitation amplitude which you get then, and you can fit it with a certain Lorentzian, and then you have a certain modulus which can be calculated from this frequency and the width, which gives you the losses more or less rather easily, and you can make a map. This is very coarse grain already, 200 by 200 nanometer, and you see the crystal as it should be is almost the same. So you have the same modulus, the same shear or bulk modulus is components of those two get together into one elastic modulus is rather homogeneous. It's a crystal, it's a single crystal. The same is actually true for quartz. If we now go to bimetallic glass, you see there is a huge variation. Actually, this is again this palladium copper silicon, and that's a certain bands actually show up here already, certain areas which have a high modulus, low modulus variation of that. And this is 100 by 100 nanometers, so each one is a 10 by 10. This color is meant to be that we make many measurements in this area, and then we assign one color to it, more or less. So it's not meant that this color and that is really sharp interfaces between the two. So it's just color coding is just more graphics. Okay, that's to say what is in this region, and then you have an average of all the measurements, and then the other one.
So these are the absolute deviations from the average. What's the average?
I showed to you the average is, well, the absolute value for the average we measure globally with ultrasound, okay? And then you see that's the deviation from that.
Okay. But I mean, so
What is the average?
The other ones were plus or minus 3%.
60 gigapascal. The model.
Okay.
What?
So sorry, 60 GPA is what you're saying.
Yeah, something like that.
So you're saying plus or minus 10 on top of 60.
I show it to you in a minute, okay? Jean-Louis is still here, so he has worked out prior to our work actually a 2D Leonard-Jones system MD simulation 2009, and showed that there is the modulus enriched, which he calls black and soft white zones also divided under strain, and this is 100 by 100 atoms, much different scale, but you see there is some inhomogeneity which nobody doubts in the meantime. But and you see that is soft and rigid areas, and you overlap then in non-defined displacement field. Obviously, where it starts, everything is in the soft spots, the soft modes, we call later on in the K-space discussion. And that's obviously the case where the motion starts, where the modulus is soft, or I will show it to you later on, even negative.
But this picture would represent like one of your boxes. This whole picture.
This whole picture will be one or more boxes, actually.
If that's one box, why aren't all the boxes roughly homogeneous? Because that looks like if you averaged.
Yes. It is right. The differences come from actually, I'll show you at the end.
There's another scale.
That's another scale. Yeah.
Is this finite temperature, or is there
Do you remember? It's
T0.
T0. Yeah. T0. Here's the numbers, okay. Now we plotted actually the frequency of the modulus which we measured over a mean value and fitted it to a Gaussian, which might be not quite true because we don't have the log plot here to get really nice ideas what it looks like, whether this is a Gaussian distribution in the landscape or not, but there might be differences. But look at the number, it's about 28% width. And this is it's 105 gigapascal. And if you crystallize it now, just use this material, crystallize it now, do it again, and the width actually goes down to 0.22%, which is in the order of our resolution of the measurements actually, and the map looks very homogeneous. We have to be careful. If you crystallize this material, it shows different orientation of the grains. You have to measure in one grain, otherwise you have different orientation, crystallographic orientations. But at least there is a factor of 100 smaller compared the width of the distribution. The width of the distribution, of the Gaussian distribution, shrinks dramatically. So in the landscape picture, if you have I draw it later on maybe again, we have a very small width obviously for the crystal, only 1 point in a single crystal in the landscape, 1 minima, but a meta basin in the amorphous one, a broad distribution. And I bring it up only, this is the loss distribution also. The losses is very broad compared to the crystal, and that's new work actually in this area is silicon dioxide. This is a strong glass, so bond orientated, which means that you cannot have such a distribution of different configurations. And so the width actually shrinks down to 2.9% if there is really Gaussian. those of you who are interested in that, you see that there is always some kind of long-range flanks over there, which is something peculiar to us. And also the losses are much smaller in the width, so the distribution is much smaller. Kramers-Kronig relation must hold anyway, so that's okay. But again, this is a factor of 10 smaller than for the fragile metallic glass.
Quick question. So you, in your box itself, you make multiple measurements, right? Each
Yes.
little box. What's the spread of moduli inside each box? Is it tiny, like 0.2?
It's tiny, very tiny.
Like 10% or?
No. It's in this order, actually.
Okay.
It's a couple of percent, okay? Yeah. It's hard to say, okay, to be honest, okay, because you have to take every time you tip up, find a new position, go down again. The force that is not allowed to be too big, otherwise you have a plastic deformation.
Right.
You have a tip, it's sharp tip. If you have one atom at the end only, then your stress on the sample it goes beyond the yield stress, and you make a nano indentation. I talk about it in a minute, okay, nano indentation. But that's not what we want to do. We want to have elastic modulus measurement, and we only touch it in the elastic regime, so the force sometimes varies from point to point. Okay, and that makes also a difference.
So how does the width of these things change with the temperature as you get?
Oh, we haven't done that. It's only one temperature measurement, the room temperature. The atomic force microscope is only stabilized at one temperature. You cannot vary the temperature.
I guess this also changed drastically with the pixel size.
Yes.
Because you don't...
It's what you expect, but you haven't done the measurement. Yeah.
Probably interesting to look at the effect of the size of your pixel on this distribution. How we,
Okay, so what did we learn? We learned that this configuration actually, which looks like a two-state model only, is in the configurations which we have is manifold. So we have lots of different configurations in the metallic glass. The width is of the distribution of the metabasins versus its depth actually is our number, because the depth is in the crystal ground state. And so we now can try to analyze actually what's going on locally for the different ones, for the strings, and then also for the avalanches. Okay, here we go again to our secondary relaxations. And this is work from Wahua Wang's group in Beijing. They analyzed a whole bunch of different systems. And what they find is that you always get these nice alpha peak. And then in the discussion of glasses and liquids, there's a group in Bayreuth in Germany, Rössler, who said, okay, we have type A and type B glasses. Type A would be some which shows a secondary peak very clearly, and type B is those which just have more or less a wing. And we have an argument now when we say, okay, it depends very much on the alloying. What we do, so little additions of a certain type of component makes a system mechanically very different. So it could be complicated, but it's so if you add, for example, a cobalt, a couple of % cobalt to it, the effect is called microalloying. It's known in plastic materials. Jack Douglas was here 4 years ago, and we stay in contact all the time about plasticizer and anti-plasticizer, microalloying in polymers. I know for you as a theoreticians, that's a horrible situation, because a 1% change changes diffusion by 70%, okay, and changes other properties as well. And the Caltech group is actually working on this glass forming ability by changing composition slightly a bit on that and this to make it really working. That's a terrible situation for a kind of universal discussion about what's going on.
But this is why this diffusion constant is somehow
measured in the liquid, with inelastic neutron scattering, Petri and others. Okay.
The reason is that there are then kind of radius barriers you have to jump over. Or
the reason is, let me show the next picture, and then I discuss it. And promise not to come back. Here's an example. Okay, you can look at this one here. Palladium, nickel, copper, phosphorus compared to the red curve, compared to the green one, which is palladium, nickel, phosphorus alone. You cannot read the numbers properly. So you add copper to the system, and then the peak shows up. And why is that? And the idea is, when you look at we talk about the heat of mixing or the nearest neighbor bonding, so to speak. If you have palladium with copper and with phosphorus and with palladium again, these three elements alone, then it looks like you have formed a very stable configuration because they are all negative heat of mixings. They are all arranging in a certain way like a molecule. If we now add nickel to it, which is plus compared to copper and 0 to palladium, strong heat of formation to phosphorus, then you see, for example, that this is this is the nickel, and if you add copper to it, then you have this one here, a strong peak. The idea is the following: we're talking about metallic systems, which has normally, you think about an S-like electron distribution, which has bonding, typical metallic bonding. It's not the case. We have strong orientations between the different bonds. And so these kind of systems, which are the early transition metals here, compared to the late transition metals, have additional cutters, or we call it cutters and glues. So in one sense, and it depends how the element you choose in which kind of matrix it is. One times you can have a glue between different clusters and form superclusters, which then show up as a separate peak. And sometimes you have a cutter in between. We call it a chain. The string, I showed in a minute, is then actually cut into smaller ones, and then the system is shifted over to underneath the alpha peak. So the type A and type B depends very much on what kind of element you add to that, and how much actually you have, what kind of is a matrix. And it means you form structures in the glass, in the liquid already, which are then extended or less extended. Like a polymer which you cut into certain segments.
So what are the numbers, the red numbers meaning?
That means the heat of mixing in kilojoules per gram atom, which is typical for the material science community. This is the strength of the bonding, okay, between the two elements.
Okay.
Yes.
So you say there is something which is loose with a certain condition?
The idea is the following. You form clusters in the liquid. These liquids have certain polyeders, okay? Icosaeders, different kinds of polyeders. And now those are the stable elements, the motifs which you try to understand. And these motifs then form either a common ones and form a very rigid matrix in the background, or you cut them up into certain segments and they are very loose, and then these are the areas where you have the soft spots. That's the idea. Pardon me? Frustration is always, I told you about the unhappy atoms. The frustration is always there because you have these kind of, you want to make a homogeneous, closed-packed system actually, right? And there is stresses in between, huge stresses, because you have orientations between the different one. If you want it as a spin glass system, then you have different orientations between the local motifs, and then they are not space filling. Density fluctuations.
The minus sign means repulsion then?
No, attraction.
But the plus is then
repulsion, yeah. Well, this is just the terminology of the material scientists.
Do you know if there's any data on glass formability?
Yes.
If some of these are better glass formers than others?
Yes, they are. Huge amount of data. The KITP group and other groups are just doing nothing else than trying that. And
I'm saying in relation to the change in the data.
Yes.
So which ones? Do you know which one offhand is better? The one with
the one which has cutters in there, where you have actually short areas. Its fragility is high. There's a PNS paper came out a couple of months ago from the KITP group, which showed that actually you have a low fragility, so more or less like orthoterphenol, and a high reduced glass transition temperature. These two ingredients actually makes up a good glass forming ability.
Is there any evidence that type temperature superposition is available?
Pardon?
Is there any evidence for type temperature superposition in this system?
Well, in the liquid there is some kind of that. High the liquid, how close to TG that still holds is a problem, I think.
These two,
The motive
if you really think there's just two sort of link scales in the landscape, like the picture, is there really any difference between these two except that those link scales are a little closer together?
So the length scales for the individual strings, which I show you then now, is actually
but I mean,
different.
There's not something fundamentally different between those two types.
Here's a string, okay? Here's a string. This is the idea of what's going on. This is from Helmut Schober many years ago, kind of a string which forms elastic follow pole and is a 20 atoms rearrangement inside a certain matrix. And the idea is the following. This, if you talk about this microalloy now, that you cut in between different parts of the string and form smaller segments, and they vibrate differently, and they are responsible for diffusion. People showed that diffusion constants depend on these kind of 20 atoms rearrangement also, and aging is also an issue which goes with the beta relaxation certainly, because you stay in one meta basin and then you just relax and can come up and forward again. This is reversible, and so the idea of this string is actually that there is some movement in the atoms, small movement of individual atoms, which makes there is no cavity for a vacancy-like type of diffusion. So there is only small motion which go upward then and triggers then the whole arrangement. And we talked too much about Eshelby. If you now move this string forward or backwards, and this is just the motion is more or less this kind of little type of motion here, you have a huge area surrounding that one, which is what we discussed during the conference and also here many times, is this Eshelby stress in the system, which is the memory of what's going on. So if you push forward, the local stress surrounding this one goes backwards. Actually, the flow of stress is coming back, and then there is a memory to come back into the old position. And so if you fix, for example, what we did with Itamar, fixing one of these atoms, pin it down in the MD simulation, and the whole beta process gets killed by 2%. So you pin only one of these atoms in a string, and its whole is stopped.
But I guess your question is about strings of arbitrary length?
No, the length scale here in the MD system is about 20 atoms. We talked about that in colloidal systems. There might be only a couple of atoms, actually, the strings. It depends from system to system.
I just was wondering if the type of A and B glasses, they don't look different to me.
Yes.
They look like you just shifted the other time scale. I think if you think of it as two time scales or length scales, either way,
yes.
I just shifted one of them.
Yes.
So it doesn't look
That's the idea.
anything inherently different between the two. Okay.
No.
Then I understood.
Sorry for. Okay. I want to make one more point for the experimentalists here. As I made in the beginning for stress and strain-driven systems, now we have somehow mechanical versus thermal noise. We had a long discussions here from our friends here, the Jean-Louis Barras group. If you do a creep measurement, and we'll do a creep measurement in the future, is actually show you that we apply suddenly a certain stress, wait for a certain time, come down again to stress 0 and wait for the recovery. So one system is just as mechanically activated, more or less, and at one point you just wait until the system relaxes by temperature. Normally you would say, okay, there is an elastic jump in the strain, and you wait for a certain time, depending on what we call sometimes delayed time, which is just a time where it reaches some kind of equilibrium, which is a matter of the loss which you have in the system, how much you dissipate in the system. Takes a certain time, you wait, and it comes back, and should be the same one. In a system which has no dissipation, these two curves are the same. Later on, I show you that on this flank we see the avalanches. On that one, we don't. So the avalanches which we discuss later on, actually, Kari knows the results, is actually only measured during creep. Whenever you do it actually in recovery mode, purely thermal, there are no avalanches. At least we don't see any. The same is true for indentation. I mentioned in the beginning, you can also make an indentation measurement. You put in really an nanodenter in the sample and measure then how much you go inside to measure something like a hardness or modulus as well. Going in, there are pop-ins, jumps. Going out, there are none. Okay, so the system behaves very different under stress, mechanical stress, and only thermal.
This all has to depend on the strain amplitude too, right? So you're in a regime where you recover almost everything, or?
That's I come to that, where it is actually. It's below. Let me. What? How am I doing in time?
You have a total, including discussion, 45 minutes.
Oh, so we have some time. Okay, great. So, to answer your question first. Well, don't jump too much. Okay. Remember your question. We come again. I'm sorry, but let's go through this now if you have some time. So you can measure now the pure beta relaxation. Just as everything is below TG, so we see only secondary Goldstein mode actually here, and we measure the delay time. Delay time is something like the loss, and then it's versus temperature and minimal stress. You measure this one. If you now apply a certain stress on the sample and have a fixed temperature, then you can see how it actually looks like in this three-dimensional picture of stresses versus temperature, and this is the losses. So your loss, if you go along a certain line here at fixed temperature, has a certain time scale also on that, which is delay time, the losses, so to speak, the log loss versus stresses at fixed temperature. You have a certain curvature, and in this kind of in the apparent activation volume, you can calculate by this simple formula how much you actually have volume activated for that process. And you can see it slow down here, and it jumps over here, and it goes here, even comes down again. So this is slope. This is plotted over here, and you put real numbers in. You find that the string volume, since we are below TG, where the alpha process is frozen out, we don't only have secondary relaxation process. We find a volume of about 0.4 nanometer cube, which is about 20 to 30 atoms. Exactly what also people saw in the simulations, in the diffusion measurements, and also in some kind of surface measurements from the Japanese group. So that is the volume we talk about in these strings, like a factor of 20 smaller than what we call the plastic events. We have a very plastic, in the simulations at least, you have a very plastic core and some kind of elastic shell surrounding that. Stefan Meyer's work, and you get 20 atoms. Or if you do it mechanically measurements, real measurements, the size is much bigger, but you include a much larger size, obviously, of the stress field, including these apparent volume measurements.
For the simulations, are those actual displacements in the particles, or are they inferring something from the inherent structures?
They show the displacement of the particles above a certain threshold for a limited temperature, and only those are plotted here. Okay? You can look at all, actually.
But these are simulations also done with creep? Or
No, this is just simulations without any.
rest?
Okay, I showed you that. I skip this spinning part and come to the avalanches. So now we're doing this. We did these kind of creep measurements all the time because we want to see how it looks like in the volume activation. And during this measurement, we saw this is just the length versus time for a certain sample again. We saw that they have some jumps in the system. Now I have to explain to you what is so different from what the modeling is doing. We have a minimal resolution of our crackling noise of 50 nanometers. The machine is not able to measure lower changes in the length scale, in the absolute length scale of less than 50 nanometers. We do have the atomic force microscope, and we do have actually a second machine which has a resolution of 1 nanometer. But Robert Ecke, who was here, also we talked privately a bit, and also he said in his talk, it's very hard to see the difference between the bus which passes by, the room motion, and everything else comes from the apparatus versus the real crackling noise. So a high resolution. We have tons of data for 1 millimeter resolution, and with the atomic force microscope, we were not able to really discriminate between those noise which comes from the machine itself and noise which comes from the sample. Here we just have a different idea. We just doesn't say, okay, we measure the slip lengths like Kai did in her mean field model. We just wait a certain time until this event happens. So we analyze these kind of in waiting time. We have the waiting time here for an event, and we say the event takes place if more ups than downs are occurring. Okay, from here there's an up. This is our jump of 50 nanometers, and we wait until we have accumulated length changes of 50 nanometers before we say, okay, this is a jump. So it's very different from what we heard before, that we see that there is a certain length change, a strain jump or stress jump. We have the waiting time analysis.
There is a fine structure which we don't see in the other.
Yes, this is the fine structure. The overall curve looks like that. If you look more closely, you see that, and if you look more closer at that one, and then there is a fine structure. This is a minute, so we have much more fine structure in there.
So
again,
this basically pushing, you're indenting your material?
No, we're pulling on it. This is a creep measurement. We stress it once, the sample, and wait. Have a constant stress, and then wait until the sample starts to creep. And the temperature is pretty high for the system, so we are below TG. We don't put that MD simulation on. This was real measurements in the moment. This is MD again. We are not in the regime of serrated flow after the yields point. We are in this region here. So it's not true that there is really an elastic material. There is already, even down here, very low stresses. We see already jumps.
Can you relate it to alpha to beta processes? Or?
That's an alpha process, which is the composure of the beta processes, as far as we can see, because we have a length change, and we can recover it to a certain amount. Not all of the jumps are actually can be recovered. Okay, there is some plastic deformation also. We cannot, to answer your question correctly, we cannot say this is actually comes from the beta process or from the alpha process. We have only 50 nanometers resolution, and we can say I can give you a number of how many plastic events, STZs, must happen before such a length change takes place. So if you look, and we're doing it also now for the MD simulation, if we look over here and getting statistics over there in this so-called plastic regimes, we find many events. Stefan Meyer did it already some years ago. So this is a local picture now. And we see locally the stress is increasing. Sorry, this is in German. And then there is a stress drop locally.
So this is
locally inside the MD simulation.
simulation.
In the simulation. Yeah, it's in the MD simulation. Stress drops.
So this is driven differently, because in your case the stress is fixed.
In our case, the stress is fixed. This is driven differently. This is changed in the affine and non-affine way. They're shearing the box, and then they see that actually.
But this is not a creep thing, is it? Or is
That's not the creep thing. It's one
just a
fixed strain, and then it's different.
At finite temperature.
And at finite temperature, and you see the numbers are very high. I don't think the numbers are really important here. It's more or less that there is some kind of a stress drop locally inside this matrix, as we saw it before. Now, what we're doing right now, to tell you that also, is measuring, looking for the motives which are prior to the jump and after the jump. You ask for actually what is going on locally, okay? So the motives which we form under stress locally, and then see how they change after the stress drop.
Is this in the beginning loading state?
Yes, it is below critical yield strain.
Yeah. Okay.
So there is almost no real elastic region in the metallic glass. They are all starting to. It just depends on the time. When you measure very slowly, you find a linear curve, more or less, like most people did. If you do it fast enough, you will see that there's activation going on, and this activation has a time scale, the beta process, I showed it to you, or the temperature scale.
Do you think that's special to metallic glasses, or that's true for all amorphous systems? I'm assuming you say that's true for all amorphous systems.
I'm with you. So I had a long discussion here again with Takeshi Egami, and I think the two of us are agreeing that there is almost no elasticity in a disordered system.
Okay, it's settled.
Pardon?
It's settled.
It's settled. I don't know. Maybe to you, but not maybe to everybody. So it's which is a problem for all kinds of other problems. The material scientists, engineers, they talk about aware, and they talk about fatigue. They talk about crack propagation, crack formation, actually, and all these things in the real systems. And how far is elasticity going on, actually? And it seems to be very limited. What was your question? I forgot it now.
A long time ago, I asked about the strain amplitude and the creep, and you just answered it. You're well below yield.
Yes. Okay.
If you,
Sorry.
how big are your avalanches if you go closer to this yield point?
Okay, we come to that. Thank you for the question. Now this is Karin's plot here from her Nature paper. And so what we're doing first is we're going very much down here in the regime stress strain curve, the so-called linear part, and then we have different parts over there. And she got this mean field result. I don't have to explain it to you. This is minus 1.5. And the cutoff, if you're coming closer to the yield stress, or yield force in her case. Okay? So we did the same now with the waiting time analysis. And what we see is actually not so much. There is only limited time in the beginning. We have only 2 or 3 decades, actually. That's very limited data. I have to apologize for that. But it looks like we get this minus 1.5, and we get the cutoff. And here you can see these absolute numbers, but we come close to the yield stress already, and we cut off then these waiting times. We're coming closer to the yield stress. There are more events. The waiting time, which is put it down here, is getting shorter and shorter, and then you get the cutoff early.
This is very so Karen has spent a lot of time trying to figure out what the distribution could look like if you've been at different levels of stress. And then it's a very strange loading mode that you're in, because you're putting it in creep near yield, but at different times during the creeping,
yes,
it's going to be behaving differently.
In their case,
right?
yeah. In their case.
Yes.
Yeah.
And I show you where we really differ. Right? You know the data, right? This is just for a certain time measurement, and that's fine.
But when you're doing the statistics, you put on the load, and then throughout the duration of the creep, you take statistics for the whole duration of the creep.
Yes, exactly.
Well, you have it on half a decade, more or less.
Yeah, it's only limited. But what now? Okay. Now we went up a bit higher in temperature, closer to the glass transition temperature, and what we observe here is what we think is a kind of a crossover from one type of deformation to the other one. Again, in the beginning, and this 90 minutes is just a number for this time of temperature. The temperature is not even shown here. There is different numbers in the meantime, and that doesn't matter much. So what we see is, again, this is a full curve of all our results, and we split it up into 2 different ones, the blue and the red one, more or less artificially, where we think the plots are going okay. In the very beginning, we see again this minus 1.5 or 1.4, whatever you want to call it then. That's around the same number. But we see a clearly different deviation from that plot, okay, from that power law. And waiting times, for long waiting times, near the yield stress, near the glass transition temperature. So it's a mixture of mechanical excitation and thermal excitation. And what we believe, what we see actually is, which is a debate. We can discuss it. I'm happy to get other numbers and other ideas about it. We see here in the mean field idea, we have all these local events, our 50 nanometer events, which take place more or less randomly. And then we need something which coordinates that into a shear band. We need to have something which are, these quadrupoles, which are lining up. We have somehow to align these ones up with a certain critical density maybe, which are then make a 2-dimensional shear band. And what we discuss here, what is a discussion, it's open actually, I make a question mark behind that. that we have from these single events, the single little shearing events, we cross over to a real shear band, to a nano shear band, which has then a different power law.
Is there anything special if you look at the creep curves and you look at the strain as a function of time? Is there anything special in any particular time?
No, nothing. Of course, this overall length change must bring up again the whole creep curve, right? There's nothing what you can see. And we see, and to make it sure that this is not we can see the set-offs. We can see the shear bands with the IFM again, atomic force microscope. We can see actually the cutoffs, the shear offsets of 60 nanometers. We find those ones actually. We find the modulus changes here. I can show you locally how the modulus along the shear band looks like. Okay, here is a very soft region. Actually, there are regions behind it. It's very clear. The shear band localizes. It is domino part of things. If one tilts the next one of the meta basin, you're coming down here. This area, you go through areas which are soft ones under this 45 or something degrees, and you can see also that there is a long-range tail of that. Actually, if you measure now with the nanodendata, this is a shear band in micrometers here, which is located there, but even far away from that shear band, you see that the hardness, for example, of the modulus is changing too. So the idea, coming back to, so this crossover, which we debated a long time ago and finally published it also, but it's not solved. Not solved. It is not system spanning ones like Robert Ecker discussed, because that would show up as a maximum, if I understand it correctly, right? He discussed that for the earthquakes. There is a change in the power law from the normal one, which is mean field discussion we had so often here during the last couple of weeks, to a very different one, which is Alain Lemaitre tells me that this is a shear band, then, but unfortunately he's not here.
So are you saying if you actually look at what happens to the sample, can you start seeing the shear bands after 90 minutes?
Well, we have no tools on doing that. We cannot do post-mortem. We cannot do it in situ. I mean, look at that.
Yeah.
The offsets can we only see the 15 nanometer offsets which come out at the end of the sample. We can see it later on, but not during the creep test.
But if you compare the sample, if you would take it out before 90 minutes and look at it and compare it with after 90 minutes.
Yes, that's what we have done. There's those offsets. We don't see any offsets for the 90 minutes before that. This 90 minutes is just an arbitrary number, right? I mean, before and after. So the idea is that we have these local, random-orientated ones, and then they form the shear band. Whether that is true or not, I don't know. And we had the discussion before, right? In several occasions. So it's still an open question for me. But it would be very interesting to see and learn more about this crossover. Do we reach a critical density of these kind of local events, and then they interact due to the HLB stress field into a coordinated, almost synchronized way, or is it just a domino effect, which you tilt one, the next one is tilted, and so on, and you go on?
So, I mean, you said you're near TG and you're near the yield stress.
Yes.
So which one of those is? I mean, could you go well below TG and see the same sort of thing?
We didn't. If we go well below TG, we don't see it. That is what the data I showed you before.
And do you have insight on how this crossover timescale here changes this crossover timescale here?
Okay, we're doing it right now. We try to see whether this scales somehow with the Fourier-Taman law, this kind of alpha excitation process. Okay.
And how does it change? So you have an applied stress, right?
Yes. Fix it.
And if you make the stress lower.
Then we see the avalanches the way I showed before. Oops, the wrong direction. We see only those. If we go down in temperature, if we go down in stresses, well, not stresses, but down in temperature, we see that they cut off. So somehow the system changes its modes of flow, is my idea actually. That there is a kind of these random, localized plastic events, and then they coordinate.
So the plot that you showed us with the crossover, for which stress was that on this plot?
I have to look it up.
Okay,
I don't know. But somehow near the yield stress up here.
Okay.
Konrad, this is waiting time or is it
waiting time? Waiting time.
It's not jump sizes.
No,
It has nothing to do with avalanche size distribution.
It's not obvious.
It's the avalanche. Well, we wait for
waiting time.
It's true, but if you had a big event, it's not unlikely, that you've relaxed it for a little bit, or you should answer.
No. The idea is that the waiting time is actually reduced, okay, to certain numbers up here for a normal event, okay. If we have now a coordinate event, this takes much longer to take its place, okay. So the idea is long waiting times means for a coordinated corporate shear band motion, which takes place then, takes much longer to wait for that. I don't know.
There's no reason at all to compare to avalanche size distribution with mean field law.
Waiting times.
No.
No, it's not obvious, because if you have a large avalanche, you can ask it, do you expect a large waiting time till you trigger the next thing after you've had a big avalanche?
A large avalanche would be a succession of steps.
That's fine. Then the succession of steps we see, a large avalanche, that would mean a short waiting time.
I think one interesting thing that could be done, this is an idea that came out of a geophysics journal club that I sat yesterday, is that you pick only those avalanches with between two size thresholds, let's say between like 100 and 1,000, and then look at the waiting time distribution between only those avalanches and see if you still get the same collapse. I think that would be an interesting thing to do.
Okay, that if we understand you correctly, you mean our binning is actually these 50 nanometers of the machine resolution. If you say, okay, we could bin, for example, other avalanches, we find maybe different distribution in the waiting time. That's what you meant?
Yeah, like you, instead of looking at all the avalanches, you only look at those avalanches lying within a certain range of sizes.
Then we
look at the waiting time between them.
But then we need when we need to get the resolution of the different steps, and then we do the normal thing. Okay, we have a certain waiting time and wait for certain avalanches. Anyway, that's too far as we can get in the moment. Let me try to summarize that also up. So we think that we see the beta relaxations as the most fundamental excitation in disordered systems, which is not speaking about the cage breaking stuff. The cage breaking stuff is in picoseconds. At least from the simulations, we know that they have a cage and the atoms move only a little bit to make from a 9-fold next Neberschaft to a 10-fold one, or so. Like Takeshi is discussing that, and this is most of the time is reversible. So these are the ones which are then change the configuration, or on its way actually, or make diffusion possible, or make aging, or make then the rejuvenation also. And these in the bimetallic glasses, we think we have that of a size of 20 to 30 atoms, at least a factor less than these plastic events. And they line up for diffusion. I didn't show you that for the small atoms, how this register works. Pinning center, Itamar showed a little bit of this work in his talk during the conference. And the crackling noise analysis gives you at least these statistics similar to the small avalanches. And then if you calculate how much slip you have for in one dimension of an avalanche of this size, we need about 300 in a row, which is quite a big number already for making 50 nanometers avalanches. And then the avalanche cross over to really nano-shear band. Okay, that's it. Thanks very much.
A little time for more questions.
Entropy. Entropy is a real question whether the potential energy landscape can be used for entropy, for the different distributions, for the different metabasins actually, and how you change, for example, if you say thermal versus non-thermal. In one case, you jump out of one metabasin into a phase space which has many of those, right? If you jump up. It's like jumping up in temperature is very different heating rates is very different, necessary to avoid crystallization and cooling rates.
Right.
Okay.
It seems like you could
so there
answer
is an
this from
asymmetry.
the simulations. I mean, the difference, the barrier that it takes for that long chain to move, it's one little step.
Yeah.
That barrier seems very small compared to the amount of time it takes for it to actually happen. Well, what's taking so long is getting everybody lined up. It's the entropy of that move that takes so long.
It's also related to all these questions we had about soft spots. So if you say that you ask, what are the fundamental relaxation when I deform a material or when I have thermal fluctuations? And people say, well, you look at the eigenvalues of the dynamical matrix. And so the question is basically what temperature you're at. Are you at temperatures where the modes of the dynamical matrix can represent the relaxations or not? And it seems like Jean-Louis may have a comment on this. Or have you mostly focused on sort of zero temperature?
We have looked mostly at zero temperature.
But I think in that in the figure that you put up, it's a very one-dimensional picture.
Yeah,
the
absolutely.
only way you can get from one point to the other in that landscape is to go over a barrier.
Right.
If you draw it in higher dimensions, you can go around the barriers.
That's the entropy question again.
Yeah, but I think
that's what I meant. Okay, if you jump upwards or you jump downwards, mechanically or thermal, actually. If you jump upwards, you have from one meta basin, you jump up into very many configurations of space. Okay, there's many of those little configurations. And if you jump downward, you cool down, you fix this position in a very fast quench, or in the simulation at least, you just go down in one meta basin, which is just that one which happens to be just formed. Okay, so there is actually a difference, a symmetry between up jumps and down jumps.
I'm a little bit dubious about your claim that an STZ needs to contain like hundreds of...
No. That's I said in the beginning, we had a discussion in this room 4 years ago what we claim is an STZ,
right,
and what we claim is a plastic event. And I'm claiming here this is, sometimes in this wording is wrong, in the sense in yours and Jim Langer's STZ model, that is 4 atoms, right, which change the configuration locally, or small amounts.
I think there are other people who claim that...
We don't talk about STZs here.
Like 20, 30 atoms, there are other people who make this claim. And I would... of course, it's a matter of how you define an STZ, but...
We didn't talk about STZs.
But I think STZs can also account for things like stretch exponential relaxation. So
say that the plastic event. It's a different story. Yeah.
I was wondering if in your creep experiment, if you actually did an extended scratch instead of having a local poke in your material, then would you have any chance to observe spatial fluctuations in the relaxation, maybe collecting information about size of the events?
No, we haven't done that actually. That's a good idea to have locally a notch or something in the sample to activate in certain regions with higher stresses. Is that what you say?
Well, I mean, if you scratch, say, on a little line and then you keep scanning this line, then you might have spatial fluctuations.
What we did is only the one which is here plotted. Afterwards, we looked for a shear band, and looked, and with the AFR technique, what is the local modulus actually around that? We find it here, okay, this shear offset, and then we can look around what is the local modulus there. It's not that easy because of this shear offset. We have to find an area where you have really no contact to the next higher step. Okay, there is a problem with the tip of the AFM. It's a technical problem.
Can we come back to your creep experiment?
Yes.
What exactly is related? I mean, why do you call these jumps avalanches? What relation do they have to the avalanches that one sees in maybe DPD programs? Or so you have jumps in the length, but how does this relate to?
Well, that's the point. We cannot do the statistics of those systems here by different length scale jumps. Okay, I mean normally you would do, if you follow Karin's suggestions, and you would say, okay, what kind of slip lengths you have for different stress, and this is limited in our case mechanically to that kind of resolution. So the idea could be, okay, you take this kind of steps and call that one avalanche if you bin it this way. Okay, that's possible. But we thought, okay, if you wait for a certain time for an event and then look for the distribution of the smaller events, the one slip event, the 50 nanometer events, they will occur more often or more different. If you pull very hard in the beginning, then the system creeps and relaxes the stress, actually, the internal stress, by these jumps. And so we just try to see whether this kind of waiting time analysis gives you some ideas about the power laws as well. It doesn't say that this waiting time, any waiting time for an event is not, gives you not the size of the slip.
Okay, that's a standard mean field.
You talk about Barkhausen laws. How should I compare this with Barkhausen?
Okay, from the statistics of the waiting times. Statistics of the waiting times is like you pull on your the magnetic system and wait until the domain was deep in. Okay, and there is a mechanic in the magnetic case. There's also creep. You have a creep relaxation if you excite the external field to a certain value and wait for the system to creep into that one. You hear also the same kind of noise from the creep experiments.
In the classical Barkhausen noise analysis, you don't look at waiting time. You look at distribution of size of avalanche,
yes,
distribution of duration of avalanche, and I'm not even scaling between both. And I'm not even sure you expect, confirm Mikhail, polar distribution of waiting time for
waiting
regular.
time is a Poissonian process.
So the classical
no, it's not. It's not.
In the mean field model, if you modify your model and put, I don't know what is a memory kernel, then of course you can get non-mean field.
Yeah,
Okay? If you have a mean field model to which he is comparing, then it's
No, I
a
think
Poisson
there
process.
may be an argument to say that his waiting times are following the same scaling law. If you basically, for example, think about the magnets. If you have long-range forces, you could imagine if you have a demagnetizing field, you could imagine that if you have a large avalanche, you have to wait a long time because you just relaxed a lot of the field. You have to wait a long time till you trigger the next one.
This
so
is not in the mean field model.
Well, he's just looking at, he's not talking about any model. He's just representing his results and saying, looking at the waiting times is
to a
just
model.
as interesting.
He's comparing to a model which
We
has
thought,
waiting times. Which
we
is
thought in the beginning there's a Poisson distribution. Okay, we thought that it would come out actually, and the results it's not.
Yeah, but the point is that it's not
You can,
because you have this interesting observation that it tells you it's a Barkhausen noise. It's nothing to do with that.
It's not obvious. I think it's not obvious.
I mean, we have to run a simulation with this process, I mean the mean field process, and then there's a coarse graining step in there, and then one has to resample this and check what comes out. I didn't do this exercise.
Yeah, we talked about that already a year ago, and yeah.
Well then, okay. I mean, if you present this data, you need to check that this has anything to do.
No, I think
At least on this mean field process.
it's perfectly legitimate to show the results and to say intuitively you might expect waiting time statistics.
No,
to relate to
intuitively, I know there is some.
But maybe I don't understand, well, why don't you just look at the distribution of jumps?
Because they are limited by our resolution. Okay, and if you have this kind of, if you call this a jump, this is 15 nanometers, this is jump, and this is jump.
All your jumps are 15.
Then we have all the 15. That's not what we want. We then have to say, okay, we must. That's what the idea. We bin those into 15 nanometer jumps and wait until time. So we call that not a large avalanche. We call that the different waiting times. It's good to see that there is
Yeah.
interest.
All right. So maybe let's thank him again for a great talk.